Hi all. I just wanted to create a video to supplement the blog that I have written about the Bitnet architecture. So as you can see that I wanted to demonstrate the capability and the architecture of the Bitnet model, right? I have downloaded this from Hugging Face. You could do that as well. And you can see that I've downloaded this particular model, Bitnet Beaver 0.58, 2 billion, and 40 is for 4 trillion tokens, right? That's basically how you expand this. And this 1.58 is the average bytes, 1.58 bytes of weights. Not all the layers in this architecture has 1.58 bits. On an average it has 1.58 bits, and that's how it is light. And also they've removed bias from the linear layers similar to your llama, so that the model becomes more inferable, right? So having said that, let me explain the architecture for you, right? So this is where your model starts. You can see that the embedding size, right? It's 128.256.2560. What it basically means is the vocabulary size of this model is 1,28,256, and each of that has an embedding size of 2560. This 128.256 is consistent with this number, right? You can see that the vocabulary size is 128.256. That is what you're seeing here, and this is the embedding size. And you can see that they've stacked 30 decoder layer here. This is a decoder only model, right, for text generation. And again, that's how it's light, right? Because generation is what they're looking at, rather than translation, where you would need encoder and decoder, right? They've stacked 30 decoder layers, one on top of the other, right? And followed by multi-layer perceptron, MLP, for that matter. And then you could also see that they're using something called bitnet rotary embedding. So this is a bit misleading if you look at it this way, because you might be wondering why are they applying this. Is basically, this is a positional embedding. Rotary embedding is, in short form, they call it rope. It's basically rotary positional embedding, ROPE. If you're wondering why did they apply that at the end, it's not that they're applying this at the end, but basically what they're doing is this will get applied at each and every decoder layer during your query and key projection. That is exactly what it means, right? Unlike your traditional positional embedding, which uses sine or cosine wave for positional embedding, which is a layer by itself, this is not a layer by itself, but it's rather a function that gets applied on top of your query and key projection. That's how it maintains the positional information. And you can see that they're using RMS prop and sublayer normalization, which is what you're seeing here, for helping with your exploding and vanishing gradient. And RMS prop helps with your adaptive learning rate by taking the moving average of the gradient, so that each and every parameter, they have their own learning rate. If the learning I mean, if the gradient is very sensitive, the learning rate is slowed down, and for the ones that are very quiet, the learning rate is made bigger, so that it learns quicker. So that's how RMS prop is applied. And you can see that they have disabled bias, like I just claimed, right? So they are removing bias from the linear layer. So this is basically the architecture of the bitnet. You can see the configuration here. So max positional embedding, right, 4096 is the maximum sequence length, right, that you can give. That is the maximum token that would be considered for generating an output. That is the configuration here. Rest of it is something that you can look at, right? Now let's try to generate some text, right? Okay, so basically what I've done is I've crafted this question specifically. So you can see what is the capital of France, and I'm also including a logical question. Also tell me what is the logic behind the statement. If it is Friday, then 4 plus 2 is equal to 6. Let's see what it has to say when it is generating. Okay. Yeah, this is where I'm generating. It'll roughly take maybe 30-40 seconds, and you can see that I'm running it in CPU, right? You can see it's running in CPU, right? I'm not moved this to GPU and all, so it will roughly take 30-40 seconds. But there is a lighter version of this called it's bitnet.cpp. That's the lighter version of it, which is compatible with C++ architecture, and that is going to be even more faster for inference. But unfortunately, I had troubles running that in Windows, hence I'm running this as a model. But if you are trying to deploy this in production, probably I would suggest deploy the C++ version, so that it is much more faster, and your inference is going to be significantly optimized, right? That said, right, yeah, it has generated the output, and you can see, right, the capital of France is Paris, which is right. The logic behind the statement, if it is Friday, then 4 plus 2 is based on a simple rule in mathematics known as commutative property. This property states that the order in which, again, right, since I've only asked it to generate 50 tokens, it has stopped. But you can see that it's doing pretty well, at least in the generation of facts, right? But logic, probably it may not do very well, because most of the logical sense, I think, from the paper, they've used a lot of synthesized data, which may have a toll on its mathematical text generation. With that, right, I'd like to close this video. Hope you like this video. Please do read the blog and then watch this video, so that you would understand the Bitnet architecture and how it functions in the backend with great depth. Thank you.